And there we go. Okay. All right, so let's just jump on in. We've got a decent amount I want to try to cover today. So remember, last time we finished off by introducing the chain rule, which is kind of this rule that isn't as straightforward as the others because it kind of encompasses all the other ones inside of it. But remember, this is essentially we have an outside function and an inside function, and we need to essentially take the derivative of the outside first, leaving the inside alone, and then take the derivative of the inside. So let's look at number 2 down here. So in this one, this is somewhat similar to the number 1 that we did the other day. So one of my screens is super laggy and the other one isn't. That's not good. Anyway, so here we essentially have, remember, and let me scroll down really quick. Oh, that didn't work. There we go. Remember, we essentially have like these 3 options for what our outside function is. Is it something to a power? Is it e to the something? Or is it natural log of something? So in this case, we're in that essentially something to a power case. This is essentially looking like some z to the 5th. So our outside function is essentially that power rule, and then the inside function we'll take care of afterwards. So the outside function, since it's something to the 5th, we have to use our power rule, which tells us to bring the power down and subtract 1 from the power. And our chain rule says to leave that inside piece alone. And then essentially once I've taken care of that 5th power, I need to take the derivative of what I have left, so that 3x cubed minus x. Well, the derivative of 3x cubed is going to give us 9x squared. The 3 in the front comes along for the ride, and then when you bring down the other 3 from the power, multiply them together, you get 9. I'm going to start writing a lot less of the intermediate steps for the things like the power rule, but please stop me and let me know if you're confused as to how something came into being. And then we have to subtract off the derivative of x. Derivative of x is just 1. Now we've taken the derivative of everything in that original statement, so we're done the chain rule. We don't have anything else to take care of, so we're good. In terms of simplifying this, the only thing I would possibly say is you could distribute that 5. Well, of course, you probably want to change the 5 minus 1 to a 4, but that's an unnecessary step. Distributing, whoop, and I didn't distribute correctly. I didn't even distribute 45 and 5. If I actually distribute the 5. That's a completely unnecessary step. Again, with these, I don't require you to, but sometimes it can be helpful for the things we'll have to do later. As with the last couple of days that we've been doing derivatives, I'm just going to kind of pause after each one and wait for questions for like a couple seconds. And if none pop up, I'm just going to keep going. So feel free to stop me when you need to. So I've got to.
Oh, I have a question.
Yeah.
Why did it go from 3x cubed to 3x squared?
Because I wrote it wrong.
Sorry.
All right, so let's scroll down to the next one before we jump over to the ones that are a bit more in-depth. Not in-depth, but have more pieces to them. So now I have the natural log of q squared plus 1. So we're essentially in that situation of having the natural log of something. So that's going to be our outside function. So if I need to take the derivative of the outside function first, I essentially need to do that natural log rule, but leave that inside as it is. So if the derivative of the natural log of x is 1 over x, then here we'll have 1 over q squared plus 1. So we've taken care of that natural log, but now I have to take the derivative of the inside. So now I need to take the derivative of q squared plus 1. So the derivative of q squared will be 2q, and then plus 0, which of course you don't have to write down if you don't want to. And you could rewrite it like this if you wanted, but again, not necessary. So we took care of the q squared and the plus 1. So there's nothing else to take the derivative of. So just to remind us, I know I was kind of doing colors last time. So kind of that first part is encompassing kind of those first 2 pieces, the derivative of f and the original g prime. And then this piece back here is the derivative of g, derivative of the inside. So now we've kind of not necessarily today, we did some the other day, but now we've gone through essentially one of each case. We've gone through a something to a power, a natural log of something, and then the one we did the other day, this problem 4, took care of an E rule. And that's essentially how chain rule is going to go, is that you kind of figure out which kind of case you're in. Are you something to a power? Are you e to the something? Are you natural log of something? And then you take the derivative of kind of that outside function first, leaving that inside piece alone, and then multiplying by the derivative of the inside. So let's do these last two. So number 5 starts off with a chain rule, and then the last two pieces aren't chain rules, but we'll take care of them separately. So the first thing we need to take care of is this 5 natural log of 2t squared plus 2. Now here, remember, we can have those cases of something to a power e to the something natural log of something up to a constant. So the fact that that 5 is out front is perfectly fine. We're still essentially in our natural log case. It's going to come along for the ride. And if I need to take the derivative of the natural log of something, we're going to have 1 over that something. So we'll have 1 over 2 squared plus 2, 2t squared plus 2. And that essentially takes care of our natural log piece. And now I need to take the derivative of the inside. So I need to take the derivative of 2t squared plus 2. So we'll have 4t plus 0. So I'm going to stop writing the plus zeros. If you want to keep writing them, go right ahead. Taking care of the 2t squared and the 2. So in terms of the chain rule that we needed for that, we're done. We're not done for the entire thing yet because we haven't taken care of those 2 last pieces. But for the chain rule on that first piece, we're done. So now we have to add on the derivative of 7t squared. So if we bring the power down, we'll get 14 t to the first. And then minus the derivative of 9, which is 0, so I'm not going to write it. Or you know what, maybe I said I'm not going to write those anymore. So the one way you could simplify this a little bit is you could multiply the 5 and the 4t together and also put it on the top of the fraction if you wanted to. Again, completely unnecessary, optional step. $14t, yeah. Did my brain do something stupid? 7 times 2, yep, okay. So here we have 7t squared, so the 7 comes along for the ride. And then the derivative of t squared, we bring the power down and subtract 1 from the power. So 7 times 2 gives what gave me the 14. Yeah. I'm just slowly moving away from writing all the intermediate steps. All right, so this last one for our chain rule section is essentially 2 different chain rules. So they're separated by subtraction, so we take them one at a time, but they are both technically chain rules. So if we want to take the... Ooh, no, don't do that, Kayla. Notice how the one thing has a denominator and the 14t doesn't. You can't add things if they don't have common denominator. So like if we had like 2/3 plus 5/3, we could totally add them together, but something like 2/3 plus 5 we can't do because it's not over 3. Same kind of deal here. We don't have a common denominator, so we can't add them together. So it would have to stay like this. P prime. So if I want to take care of this next one, the first thing I need to take care of is this e to the something rule, essentially. That 2 comes along for the ride. And then if I have e to the something, well, what's our e rule say? It's essentially saying, it essentially tells us that the derivative of e to the, z is e to the z. So we're going to have e to the x squared plus 7. But then I have to multiply by that derivative of the x squared plus 7. So I've taken care of the 2, I've taken care of the e, but I haven't taken care of the derivative of the x squared plus 7, which will give us 2x plus 0. So since it's just plus 0, I just won't write it. And now we've taken care of the x squared and the plus 7. There's nothing else to take the derivative of. There's no more inside functions, so we're done. That piece. And then I have to subtract the derivative of 5 natural log of 2x minus 1. 5 comes along for the ride. Derivative of natural log of something is 1 over essentially that inside piece, and then we have to multiply by the derivative of the inside. So we've taken care of the 5 and the natural log. Derivative of 2x is just 2. Derivative of minus the derivative of 1, which is 0, so I'm just not going to write it. So we've taken care of the 2x and the minus 1, so we're done all of the pieces in that chain rule as well. If you would like, you can simplify this a little bit. You could multiply that 2 and the 2x to get 4x e to the x squared plus 7. And you can multiply the 5 and the 2 to get, whoa, what have I done? To get 10 over 2x minus 1. But again, if you stopped here, that's perfectly fine. You can totally stop there and that'll be acceptable. Questions, concerns on the chain rule before I move on to our next set of rules? Our last 2 rules, I should say. They're the last 2 we've got. I'll hold on like 5 more seconds. All right. So our next 2 rules are the tiniest bit similar to the chain rule because they are both kind of the same thing where all the other rules kind of work inside of these rules. But they're nicer than the chain rule because they follow a bit more of a direct pattern. So here's our last 2 rules. We have the product and the quotient rule. So the product rule is for when you want to take the derivative of essentially 2 functions that are multiplied together. And I'm going to run out of space if I keep writing that way, so I'm going to jump down here. And I'm going to, kind of like I did with the chain rule, I'm going to jump to the different type of notation. So we're going to have the derivative of f times the original function g plus the original f times the derivative of g. A lot of times I will just say this as f prime g plus fg prime and just the of x's. A little tedious. But technically the full out rule has the of x's sitting around there. But essentially we take the derivative of the first function, leave the second function alone, and then add that to the first function left alone times the derivative of the second. Quotient rule is for when we have 2 functions, one is divided by the other. What this is going to give us is a fraction. So we're going to have f prime times g minus f times g prime. So essentially this a very similar setup to product rule, just with subtraction instead of addition. But then we divide by that bottom function all squared. Not the second derivative squared, just regular old tack a squared on it. So I'll hold on for like 5 seconds so y'all can get that down. All right, so the first one I want to do is kind of just to illustrate that the rule works the way we think it should, because if I were to multiply these together, I'd get x cubed. And if I took its derivative, I know that I would, if I take a derivative, if I write it like that, just because I'm running out of space, we think that we should get 3x squared. So let's try to use the product rule to get that. Now, I personally kind of like coming off to the side and doing a kind of chart, if you will. Juliana, I don't have a better answer for you than just that's what it is. Giving you a proof of why that is very complicated. This is a trust and believe me type moment. Just trust and believe that it's supposed to be squared. But anyway, I like to kind of come off to the side and do a little chart. It's not necessarily, what am I saying? I don't know. So what I like to do is I like to kind of come off to the side and do this little chart. It's kind of more helpful when you have more complicated problems than just this one. But I kind of like to come off to the side and say, what's my one function? What's my other one? Oh my goodness, my words. What are my two derivatives? So what's the derivative of x? It's 1. What's the derivative of x squared? It's 2x. And then once I kind of have that kind of chart kind of off to the side, I can kind of just put it in that format of f prime g plus fg prime. So my derivative would be 1 times x squared. So I'll write it out in full generality, even though I would just write x squared. And then x times 2x. Yeah, Juliana, there's not. It's just what it is. What was I going to go for? Oh yeah, you don't have to do this little chart off to the side, especially like if you've seen derivatives before and you already have a way that you like to do it. A lot of people will just say, okay, this is my first function, this is my second function, then just write it out as they go. They'll say, well, what's the derivative of x? The derivative of x is 1. And then I just have to multiply it by g, which was x squared. And then I have to have f, and then g prime. What's the derivative of x squared? It's 2x. And they'll kind of just write it out as they go. I just kind of think the chart off to the side just makes things much more clean, in my opinion, but whatever floats your boat. If we were to simplify this a little bit, we would get 3x squared, which is exactly, again, what we thought we should get because this actual function is x cubed. So its derivative should be 3x squared, which it is. So hooray! So that's how product rule works. Let me go through another one of those before I jump over to quotient rule. And we'll do one of those then. So this is what I mean by, this is almost slightly nicer than chain rule because it follows this set pattern. You just need to find the little pieces and then just put them together. So say I have x squared times e to the 2x, and say I want to come off to the side again and I want to do my little chart. So I have f and I have g. Now, if it freaks you out that I'm naming this f, but the function's name is f, you can use whatever letters you want, a and b, c and d, x and y, whatever floats your boat. But I find that most people don't really care. They kind of get the difference. So now I need to find both of their derivatives. So it's the derivative of x squared. Bring the power down, subtract 1 from the power. We've got 2x. What's the derivative of e to the 2x? Now, actually, I'm going to take a kind of side note here. Not really a side note, but. So we had an e to the kx rule. But remember, way back when we learned that rule, I wrote off to the side, this is technically a chain rule. So I'm going to pretend that I don't have that e to the kx rule, and I'm going to treat this like a chain rule to show you that it is a chain rule. So this is technically an e to the something. So the derivative of e to the something is that e to the something, but then I have to multiply by the derivative of that 2x. What's the derivative of 2x? It's 2. So this does come out to be exactly what I thought it was going to be. 2 times e to the 2x using that e to the kx rule. But I just wanted to clarify that, once again, that e to the kx rule is technically a chain rule. So anyway. So now I've got all my pieces, so now I've just got to put it in the correct format of the f prime g plus fg prime. So f prime times g, so we have 2x times e to the 2x. You don't have to write that multiplication symbol in the middle. I'm just trying to be super duper clear. And then f times g prime. Could totally leave it right there if you wanted to. Personal preference, I like having everything with the e at the back, so I would, and I like my constants in front, so I would rewrite it like this, but whatever floats your boat. So that's that one. So now let's jump over, if there are no questions on those, to these quotient rules on the side. on the other side. So the first thing I want to do is I actually want to do number 5 in 2 different ways. So the first way I'm going to do it is with the quotient rule, because this is technically e to the 2t divided by t. So I would do a similar type of chart here. But here we also need a g squared piece. Sometimes I'll forget to put the g squared piece in my chart, just because I remember to put it in the final rule. But so what's the derivative of e to the 2t? Well, that's going to be 2e to the 2t, either by the e to the kx rule or that similar kind of chain rule way that I just did down here. What's the derivative of t? It's 1. And what's g squared? Well, if g is t, then g squared is t squared. And then if I need to put it in the derivative, so it's, again, a similar format to the product rule with f prime g and f g prime, but now we're subtracting the 2 instead of adding. So f prime times g minus f, I'll put times for clear. Again, once we get going on these for a while, I'll stop writing that kind of extra stuff. But for now, I'll put it in there. And then divided by g squared. Now, so hold on for just a second. Now, technically, we can always do product rule instead of quotient rule. There were some people that I went to school with that absolutely just downright refused to use the quotient rule. I don't quite get it, but whatever floats your boat, because essentially what can happen is you can rewrite the original function, and you can take that thing that's in the denominator and put it to the negative first power. Now, for this one, it works out kind of nice because it doesn't come out to be something super gross to the negative first. But say you were working with something like this down here with the q cubed plus 1 in the denominator, that would then put you into a chain rule situation. So if you decide to do these ways where you change it over and then do the product rule, just know that you're then going to have to also use a chain rule. But anyway, so I could do it this way, and now I treat it as a product rule instead of a quotient rule. So I have t to the negative first, and what am I doing? And then f prime and g prime. We've got 2e to the 2t. And then a power rule here would be negative 1t to the negative second. So then our derivative f prime times g plus f times, oh no, let me get rid of that negative 1 then and just write negative t to the negative second. Ooh, that's squished. Let me try to rewrite that over a little bit. Let me zoom in so I can maybe write a little bit better. So the full derivative 2e to the 2t times t to the negative first plus e to the 2t times negative 1t to the negative second. I'm assuming it doesn't matter which order you put the 2 multiplications in, right? It depends on exactly what you're meaning there, but most likely the answer is no. So if you're talking about f prime g plus f g prime versus g f prime plus g prime f, those are perfectly fine. Now with product rule, you could also, you know, switch around the things that you're adding as well. The only thing I want to be super careful with is you can't do this kind of switch in quotient rule with the changing around. So the difference between that and that. So f prime g plus fg prime versus fg prime plus f prime g. You can do that in product rule because the two things are added together, and you can, 2 plus 3 is equal to 3 plus 2. But in the quotient rule, you couldn't. So be careful with that. But in terms of just switching around, like which one you're multiplying by which first, that's perfectly fine in either rule. So you can even do that in quotient rule. Instead of f prime g, you can write it as g times f prime. That's perfectly fine. Yeah. Yeah, so yeah, if you do g times f prime, that's perfectly fine. Because when you multiply two things together, it doesn't matter what order you multiply them in. So now again, that's kind of like two options. Again, I personally don't really get why people don't like using the quotient rule. I think the quotient rule is, I mean, it looks scary, but once you've done it enough, it's, maybe I should avoid the word simple, but it's the only one coming to mind. It's not as freaky as people think it is, I think. So I don't really usually jump over to using the product rule in these cases, but if you want to do that, if that's what floats your boat, go right ahead. But anyway, that's probably the only one I'm going to do in both ways. Also, I should just say, notice that these two answers don't really look very similar. The one has a denominator and the other one doesn't look like it does. But if we did a bunch of algebra on either one of them, we make it look like the other. So they are the exact same answer, they just look different. Anyway. So now I'm just going to go back to using the quotient rule. But just know that it's an option. It's just that that option will also bring in a lot of more chain rules than you would have if you just did quotient rule. So let's look at this next one. We've got f is 5q squared and g is q cubed plus 1. So f prime would be 10q. 5 comes along for the ride. The 2 that gets brought down gets multiplied by it, gives us 10. And then we would get 3q squared plus 0 technically. And then g squared, let me shove it in over here. Q cubed plus 1, just tack a squared on it. Don't even worry about simplifying it, just tack a squared on it. So then our full derivative times g. If your thing, any of these terms, if it has more than one thing, is it, nope. If there's addition or subtraction in any of your kind of terms over here, like we have in G, please put it in parentheses or else you're gonna not be right. And then minus f times G prime all over G squared. Of course, you could simplify that a little bit. I'm out of space, so I'm just gonna leave it. All right, now there's, oh man, 4 more here, but I want to move to a similar idea, just, oh my gosh, why is my English not working today? I'm going to move on to something else. We'll come back to the other ones most likely on Monday. We'll catch everything that we missed, but because some things from the next page show up on your homework, I want to get to that. Can I simplify it? I guess I'll just have to erase it because it's going to run into the next problem. So if this were me, I would just focus on simplifying that last term. I would probably personally leave it here, Juliana, but technically from here you could also distribute that 10q, so 10q to the 4th plus 10q minus 15q to the 4th. And then you've got two things that have a q to the 4th, so 10q to the 4th minus 15q to the 4th. So 10q minus 5q the fourth divided by the q cubed plus 1 all squared. I don't think there's any more algebra we could do on that, because if you expand that out, that would be gross. You could pull a 5q out of the top, but it's not really going to simplify it anymore. So yeah, I would leave it there. I probably wouldn't do much more than that. So now I'm going to erase it all because whee! I wish there was a better erase option on this where I could just make a whole section disappear. But so again, we'll come back to these later, possibly on Monday, but I want to come down here eventually. There we go. To problem 10, because ones like these show up on your homework, so I want to make sure you can do it before Monday if you want to. Oh, Kayla, memorize. Yes, you will have to memorize all of the derivative rules. It should be a fact that you've used them so much that they should start to slowly get memorized anyway. But yes. So let me split this up. Now, nudge, nudge, wink, wink. I really love these types of questions. Because unlike the ones we were just doing, this really makes sure that you know exactly what's going on. So first of all, let me just remind us, because we'll need the chain rule here, so let me remind us of what our chain rule says. It says the derivative of the outside evaluated at the inside times the derivative of the inside. So what we have here is we essentially have two functions that are set up to be compositions. We have f of g of x, and then we have g of f of x, and we want to find the derivative of those functions evaluated at a certain point. So the first thing I want to find is I want to find h prime of 1, where h of x is f of g of x. So the first thing I should probably do is just find the generic, the generic derivative. So we don't actually have an equation here, but we do have a format that we can use the rule on. Now the nice thing about this one is that it exactly mirrors the chain rule, so we can kind of just rewrite it, but also kind of think about what the derivative of a composition is. It's the derivative of that outside function, leaving the inside function alone, and multiplying by the derivative of the inside. So if you think about it, if prime of 1, well, then you just plug in a 1 everywhere you see an x. And remember back from when we talked about compositions for the very first time, whenever you're working with compositions, it's inside out. So we would want to focus on this g of 1 first. And now I go back up and I say, okay, well, what am I told g of 1 is? I'm told g of 1 is equal to 0. So I can replace that with 0. And then I need to find f prime of 0, which is told to be 0. Lots of colors in here to help us figure out where things are coming from. And then g prime of 1, we're told, is equal to 1. So we've got 0 times 1 is 0. Juliana, you're kind of on the right track there. You should, this stuff that we're doing here, it seems super fresh and new right now, but it's going to be used so often that you're just going to start doing it without realizing that you've already memorized it. The next exam is coming up somewhat quick. It's on the 21st, so not next week, but the week after. So it is kind of creeping up on us. Are there questions on this thing that's up here now? So essentially what we had to do is we had to take the derivative kind of very generically and then just replace these values with the things that we were told in the given problem. So now let's do the other one. So we're calling this k prime of 1, where k of x is essentially the opposite composition, if you will. It's not really formal language for that, but. So if I want to think about what the generic derivative of that is, think about what the chain rule tells you. What the chain rule tells you is to take the derivative of the outside, which in this case is g. So the derivative of that outside function, leave the inside function alone, times the derivative of the inside function. Once again, we want to work inside, well, no, hold on, I gotta write that down first. So if I want k prime of 1, I'm going to replace all of those x's with 1s. And remember, with these compositions, we want to work inside out. So what is f of 1? It is coincidentally also equal to 1. Oh, I forgot to replace that with a 1. Whoopsies, whoopsies. And then, have I colored these already? That one's already been colored. So g prime of 1, and then I need a new color for f prime of 1. Pink, I guess. So we've got g prime of 1 is equal to 1, f prime of 1 is equal to 3. 1 times 3 is 3. Questions, concerns on that? And again, nudge, nudge, wink, wink. I really like these ones. Okay. For the sake of time, for getting in one more thing that I want to, because there's another type of question that's very similar to this, but includes graphs instead of just given values. So there's another one like this. We'll go over it on Monday. It's a very similar thing, except for now we're going to use our product and our quotient rule. So it's the same type of idea of you set up the derivative generically, and then you just plug in the values where they're needed. But there's a different type of question for the same kind of idea, where we're given a graph, and there's a few of these on your homework as well, which is why I wanted to get to it today. So, and again, we'll hit everything that was skipped over or missed today, we will hit on Monday. So for the sake of time, to try to get to ones that look slightly different than the ones we just did, I'm going to start with number 3. Also, for some reason, these functions weren't labeled. I thought I labeled them, but they weren't. So the blue one is going to be f of x, and the orange one is going to be g of x. Yeah, Sam, it probably won't be up until later today because I have classes right after this and then a bunch of meetings, but it will be up eventually today. So say I want to do a similar idea to what we just did, where I want to find h prime of 2 if my h of x is essentially a product of f and g. Now, because I have so little space on this one, I'm going to find the generic equation and also plug into at the same time. Well, actually, maybe let me just come down here. I'll do it down here. I'll write the generic derivative for number 3 down here, just because this is the one I'm working on first. So that's a product rule. So what does our product rule say? It says take the derivative of f, take the derivative of the first thing, times the original second, plus the original first, times the derivative of the second. I don't know why I put a multiplication symbol there and not the other one. So if we want that evaluated at 2, well, let's just plug in 2 everywhere. Plus f of 2, g prime of 2. And now I need to figure out a couple values. So notice, oh, hold on a second. Sometimes I gotta remember that y'all can't write at the speed that I do because you gotta wait for me to be done. We've got two things that are essentially the original functions, and then we've got two things that are derivatives. So on our graphs here, if I want, say, g of 2 or f of 2, well, that would just be, you know, these points, these y values on the graph. So what is f of 2? Well, f of 2 is 4. And what is f of, no, sorry. What is g of 2? G of 2 is 6. So we know that g of 2 is 6 and f of 2 is 4. So I can plug those two values in. And let me clean my phone. Now I want to talk about the derivative. Remember, the derivative tells you slope. So essentially what this is asking for is the slope at 2, for both functions. Now both of these functions are made up of straight lines. So let's find the slopes for these straight lines. So let's focus on f of x first. Let's focus on this piece right here. What is the slope of that function, that line? So if I start here, if I jump over, I would have to jump up 1, 2, 3, 4. So I went up 4, but be careful with the units on the x-axis because that went up by 2. So I went over 2, up 4. So the slope of this line, so I'm going to write it here, would be 2. Let me focus on g of x now. It's the slope of this line. Well, if I start here, I go over and then down 2. So I went down 2, but again, be careful, the x's go up by 2. So then the slope of this line would be -1. And because we'll need it in a second, because I'll try to do this number 4 afterwards, this piece here, what's the slope of that piece? Well, that's a straight horizontal line, so the slope of that would be 0. So essentially what this means is that absolutely any derivative value for f between 0 and 4 will be equal to 2. Any derivative value for g of x at all, because it's just one straight line, is going to be -1. And the derivative value for f between 4 and 8 would be equal to 0. So if I want f prime of 2, my slope at 2, since it's on that kind of first part of the line, that slope is 2. And then the slope of g, so the g prime of 2, the slope of g of x at 2, since the slope of g of x is the same everywhere, that'll be -1. I've run out of space, so I'm going to have to kind of go backwards here. So 6 times 2 is 12, minus 4 is 8. So the value we're looking for here is 8. So we used our product rule kind of in a more generic way than we were doing before to be able to find that value. So I want to do one more. I'll do 4, and we should hopefully have enough time. Got 5 minutes to do that. So I want k prime of x, where our k of x is this quotient. So we essentially need to write out our quotient rule generically. So that says the derivative of the first times the second plus minus quotient rule. The first times the derivative of the second divided by the denominator all squared. So essentially what I'm going to want is I'm going to want all of those values evaluated at 6. So f prime of 6, g of 6, minus f of 6, g prime of 6, all over g of 6, all squared. So once again, we have some regular values and we have some derivative values. So we've got, we've got a regular value here, a regular value here, and a regular value there. And then derivative values here and here. So if I start looking for these values, because now that we have all the slopes written out, we've done most of the hard work. So f prime of 6, well, if 6 is here, and I want the slope of f of x at that point, well, that means that we're on kind of that horizontal line part of f. So the slope of that's going to be 0. So we're going to have 0 times g of 6. What is the y value of the function g at 6? That'll be 2. Minus f of 6. So where's the function f at 6? Go to the function at 6. That is over at 8. Times g prime of 6. What's the slope of the function when g is at, what is the slope of g when x is 6? Since the slope of that entire line is -1, that'll be -1, so 8 times -1. G of 6 was equal to 2, so we have 2 squared in the denominator. So we'll have positive 8 over 4, so 2. The final answer of 2? There's a couple 2's floating around. Two squared. So Kayla, the 2 squared, I needed g of 6 in the denominator. So what is g of 6? Well, let me go over to 6. Let me go up to the function g. Well, that's at 2. So since g of 6 is equal to 2, that's why that got replaced there. Catherine, how did I get 8? The positive 8? So here I essentially have 0 minus -8 over 2 squared. So the minus -8 is what makes it a positive. So Gwen, I think that also answers your question, since I have a -1 there, but also a minus sign. Those two essentially cancel each other out. I think. Catherine, did that answer your question, or was it how did I actually get that value? No. So that 8 that's appearing there comes from the f of 6. Let me try to bring some more colors in here again. So the g of 6 gave us 2, and the f of 6 gives us this 8. So that was coming from f of 6. So that was saying, let's go over to 6. Let's go up to the function f. What is our y value is 8. The slope, the 2 slopes that I have in here are the 0 and the -1 value. Does that make sense? Right. Is it, let me zoom in a little bit because they're tiny. Does it have a prime or not? Does it not have a prime? Does it have a prime? If it's got a prime, this is the slope. If it doesn't have it, I put that in the wrong spot. If it doesn't have a prime, it's the y value. So the derivative versus the original function. All right, so we are out of time. I know this was kind of a hefty day. I was jumping all over the place. We had some new rules and all that jazz. If you have any more questions, feel free to stick around for a little bit before my next class. Otherwise, have a good weekend. remember your homework's a little weird where you have the official stuff on Wiley. There's only 9 questions, and then there's the derivative practice on Blackboard. That's more like this stuff because Wiley doesn't handle this stuff well. So there's both, and I would definitely suggest at least doing a subset of the ones that are on Blackboard. That's why your Wiley is shorter this week. But anyway, I'm done now. I will stop the recording. If you have questions, let me